Speaker virtually, please welcome Shyam Sunder Lakesar.
Hi, I'm Shyam from Indian Institute Technology of Kanpur. Today, I'm going to present my work on lower bound, or you can say lower cutoff voltage for transmutation using half-wave rectifier in light water electrolysis. One of my research guide, Professor Raj Ganeshpala, is available in offline conference as a second speaker. So, let us begin with experimental setup. As you can see from the figure, we have used variac transformer to control the applied potential and a half-wave rectifier for unidirectional current to power the reaction. From our experience, non-steady potential gives better transmutation results than steady DC potential. Here you can see we have used 6 mm diameter graphite rod of 99.99% carbon composition for all electrolysis at different voltages, and 1 mm diameter nickel wire of 99.5% nickel and 0.5% iron of composition is used as cathode. We used 1 molar potassium carbonate aqueous solution. Current and voltages are monitored during the reaction. As you can see in the second image, I have used plastic insulation on cathode. So let's first watch a short video and understand main motto behind this. So this is clear how insulation makes difference. Without the insulation, a reaction is very violent and solution keeps spilling out of the beaker. So to prevent the spilling, insulation is used and it gives us freedom to dip the cathode deeper inside the solution. And effective reaction area can be controlled by adjusting height of insulation. Here, the insulation is a hydrocarbon polymer. Now, let us look at cell parameters. So, here, the electrolytic cell parameters. For each reaction, both cathode and anodes are kept 1 centimeter away from each other and dipped 1 centimeter in the solution. And electrolysis is performed for 120 minutes at each voltage. Before electrolysis, cathode and anodes are properly cleaned using various chemical treatments. Now let us move to a sample analysis. After the electrolysis, electrodes are pulled out of the solution and cathode is rinsed with deionized water to remove potassium carbonate present on the cathode surface, as it will appear in further analysis. For the analysis of cathode, energy dispersive X-ray analysis (EDX) technique is used. For each analysis, 50 by 50 micrometer area was analyzed at different locations. As you can see in the figure, I am referring to body and tip. So this whole inclined part of cathode, I am referring as a tip. These are just notation to show the area on which analysis was performed. Now, let us move to analysis results. Let's analyze this bar graph. So these results are on body area, which you can see in the figure. Here on x-axis we have applied potential and on y-axis we have relative weight ratio. For convenience, I have excluded nickel weight ratio. Here, orange bar refers to the copper weight ratio, yellow bars refers to the gold weight ratio, and grey bar refers to the platinum weight ratio, and black bar refers to the iron weight ratio. So here, Clearly, we have a new element which is copper has appeared in analysis, and weight ratio of iron also increase. For increment in weight ratio of iron, we have some assumptions that iron is or it may be migrating from the bulk to the surface. We have seen increment in iron with different nickel sample, which was 93% nickel and 7% iron. With this sample, almost 100% iron was observed on the surface. If we scratch the sample from the surface, the iron will be removed from the surface, and if we analyze that sample back, we will get the original composition, which was 93% nickel and 7% iron. So from this, we are predicting that iron may be migrating from the bulk to the surface. Now let us move to the more exciting results on tip. You can clearly see here we have huge amount of gold on tip, almost at all voltages. Also, some platinum is also appeared, but here ADX machine resolution is limited, so machine is clearly not able to distinguish between gold and platinum ADX peaks. So here you can see weight percent of gold at different voltages, which is quite significant. Now let's look at some different results also. So here you can see some glow discharge on cathode with different electrolyte solutions. We observed glow color is close to flame test color to the corresponding cation present in the electrolyte. As we can see, for potassium carbonate solution, glow color is close to lilac. For sodium carbonate, it is yellow, and for lithium carbonate, it is close to crimson red. Colors may seem different in the video, but in real, they look close to the flame test color. As all the electrolytes have different solubility and they have different voltages after which the glow will appear, we have to go beyond a certain voltage to see the glow. For potassium carbonate, it is 20 volts. For sodium carbonate, it is 40 volts. For lithium carbonate, we have to go beyond 100 volts. Now we have some open questions for which we would like to hear from audience. As you can see from the results, there doesn't seem a lower bound voltage in range 1.4 to 45 volts. Then is it possible to have cutoff voltage in terms of time or transferred charge? We also have seen a glow on cathode. So what causes the glow? How the glow is related to the temperature of the electrode? How glow is related to temperature of electrode when there is a glow? Why there is a huge transmutation on tip, and what makes tips so special? On body, iron weight ratio increased significantly. So is it actually migration of iron from bulk to surface? If there is elemental transmutation, is there possibility of emission of gamma photons? For this, you can refer to poster number 25 of Ankit Kumar on correlating transmutation to excess ionizing radiation in light water electrolysis under steady and periodic high potentials. Does hydride formation helps transmutation, and can electron beam interaction with hydride have transmutation? For this, you can refer to the presentation of Monu Kumawat about trends in transmutation products and hydride formation in brass, bronze, solder, silver brazing, alloy cathodes during light water electrolysis. So let us move to the conclusion part. From multiple times repeated experiment and repeated analysis suggest there is no lower bound voltage for transmutation in nickel within 1.4 to 45 volts voltage range. So for voltage range 1.4 to 45 volts on body, or you can say longitudinal part, copper is main transmutation product, and On the tip, gold is main transmutation product. Now from figures, we can clearly see how much gold and how much copper was found. Thank you.
If anybody has any questions, feel free to go to one of the mics on either side for a quick Q&A session.
So, two questions. First one, you have DC electrolysis or unipolar AC electrolysis? First, you have DC electrolysis or you rectify the line to have unipolar with zero crossing?
Yeah, yeah. I use the AC line and I use half wave rectifier to rectify it.
Can you repeat? I don't understand. Can you repeat, please?
Yeah. We
Slowly.
just use. Okay.
Thank you.
So what we do is we use variac transformer to control the voltage, and then afterwards we use the half wave rectifier to click the negative part of the waveform. So we just use positive part of the waveform.
So you have zero crossing of the current from 0 up to the maximum and 0, 50 Hz like. Okay.
Yes.
Moreover, did you make a cross-check of your results using ICP mass instrumentation? ICP mass to detect if really gold or iron and so on.
Yeah,
Did-
that we are going to perform next.
Okay, thank you.
Hello. This is
Yes.
John Brandenburg from Kepler Aerospace. These are quite remarkable results, and we will be trying to reproduce them. Let me ask you something, though. I'm not an economist, but if you have patented, I hope, this thing for making gold from nickel.
That is not a very economical thing to produce gold in that way.
It is not cost effective at this point?
Yes, that it is not cost effective.
I see. Thank you very much. But this is an extraordinary result. I cannot wait to reproduce it.